that off. Well, good afternoon again. Welcome. I'm Lori Leshin. I'm the president of the Planetary Sciences section of AGU, and I want to welcome you to the first of 3 named lectures from our section at this meeting. In addition to what is going to be a fabulous lecture today, I also invite you to join us right back here in this room tomorrow morning from 8 to 10 a.m. to hear 2 more fabulous named lectures, one by Jeff Marcy, a pioneer in exoplanets research, giving us the latest on planets around other stars. And that'll be followed by Sean Solomon, who will give us the latest news from Mercury. So it'll be very exciting tomorrow morning, 8 to 10. Please join us. Today, I'm very pleased to introduce and honor this year's Whipple Award winner. The Planetary Sciences section Whipple Award honors an individual who has made outstanding contributions to planetary science. It is the highest award given by the AGU Planetary Sciences section. The award is, of course, named for Fred Whipple, a gifted space scientist most noted for his work on understanding comets. We have selected Joe Veverka, the James A. Weeks Professor of Physical Sciences and Professor of Astronomy at Cornell University, as this year's Whipple Award winner. I believe this is especially appropriate not only because many of Joe's major contributions to our field have been in the comet arena, but also because, in fact, Joe was Fred Whipple's last graduate student. Joe's contributions to planetary science have been in fundamental research on the surface properties of planets and primitive objects, in holding key leadership roles in planetary missions, and in his exemplary service to our community. Joe has been a pioneer in the use of photometry and the development of photometric phase functions from telescopes and spacecraft to characterize the nature and physical properties of planetary surfaces, focusing especially on small bodies. He has led, along with many of his students and postdocs, important studies that enabled albedo determinations on asteroids, comets, planets, and satellites, and thus the direct comparison of their surface properties to laboratory data sets. In addition to his amazing contributions in research, Joe has been involved as a PI, team leader, and key co-I on a remarkable number of robotic space exploration missions, including Mariner 9, Viking, Voyager, Mars Observer, Galileo, Mars Global Surveyor, NEAR, Cassini, Contour, Deep Impact, and Stardust-NExT. I'm exhausted just reading the list. Joe has also performed important committee and service work for our community, including serving as an editor at Icarus, chair of many NASA working groups, chair of the National Research Council's Committee on Planetary and Lunar Exploration Complex, and most recently as chair of the National Academy's Decadal Survey in Planetary Science Small Bodies Panel. Beyond these academic and community achievements, Joe has been an outstanding teacher, advisor, and mentor to many of the leaders in our field. Joe's service to NASA, to his colleagues, and to his discipline exemplifies the selfless service that AGU values as a model for its members. He is qualified in every respect to receive the Fred Whipple Award, and it's my great pleasure to welcome him to the stage to accept the award and present the Whipple Lecture, which is entitled The Complex Evolution of Comet Nuclei, Evidence from Deep Impact and Stardust-NExT. Joe Veverka.
Thank you very much, Lori. And, let me just say that it's a great pleasure to receive this award, both because of the recognition it represents on your part, my colleagues and friends, and also, as Lori mentioned, because, oh, there we go, and that's what we did. And also because, as Lori mentioned, I was Fred Whipple's last graduate student. After dealing with me, Fred gave up on graduate students. But folks, I'm delighted to be here this afternoon to talk about comets. Let me say specifically that I will be talking about comet nuclei, and even more specifically, I'll be talking about the geology of comet nuclei, where we have recently learned and are learning a lot of things. Now, as is the case in most endeavors where you're learning things, there are really 3 steps involved. At first, when you know nothing, you think you understand everything. The second step is you begin to gather a lot of information, and you get confused because you don't have the big picture. And of course, the third step is you hope eventually to get the big picture and fit everything into a coherent, understandable whole. Well, I confess at the beginning that we have only reached the second stage. So if you expect enlightenment today, you will not get that. You will get a lot of information about comet nuclei and a lot of questions about comet nuclei and some confusion. So with that, I will begin with a little bit of history and just remind us that it's about, I guess, 60 years ago that Fred Whipple, indeed, proposed that a comet nucleus is nothing more than a dirty snowball, and that it was in 1986 that this idea was confirmed by the first spacecraft encounter with a comet, the Giotto flyby of Comet Halley in 1986. Now, Giotto was extremely successful in terms of telling us a lot of things about comets, but in terms of spatial resolution of its images, that was very, very limited. So we didn't really learn very much about the geology of a comet nucleus. And even with the second comet encounter, which occurred in 2001, we still were kind of in the dark. And our ideas about comet nuclei are very simple. As this sketch suggests here, these are some Halley-era ideas of what a comet nucleus might look like. They all consist of various versions of a comet nucleus being made up of agglomerations of ice and dirt in various mixtures, but actually not very much geology involved in this. And as I mentioned, even the second encounter with a comet nucleus, that with Comet Borrelli by the Deep Space One spacecraft in 2001, it did a little bit better resolution, told us a little bit more about the morphology of a comet nucleus, but still, the models of what a comet nucleus is like were rather primitive. We're still back to this idea that a comet nucleus is basically, again, an agglomeration of chunks of ice with dirt mixed in, and as some of the ice evaporates because of sublimation, you get left behind on the surface a covering of dark, non-volatile material consisting of organics and minerals, making the surface of a comet very, very dark. But again, in terms of geology, there really isn't very much to talk about at this point. And that picture, that simple picture of comet nuclei, didn't change really until 2005, when the Deep Impact spacecraft on July 4, 2005, flew by this object, comet Tempel 1, an object which is about 6 kilometers across, rotates very, very slowly, and now, instead of having a resolution of 40 meters per pixel, we have a resolution of 4 or 5 meters per pixel, and we can begin to see that this is, in fact, a geologically interesting and complex nucleus. And if that's not clear, I'm going to show you a cartoon of the same picture, where in different colors, we have identified geologically different and interesting features. First of all, let me call your attention to 2 of the yellow areas here. And these are very, very smooth surfaces where material has apparently actually flowed downhill, having been extruded from the interior of the comet. There are also places, shown in blue here, where exposed are fairly thick layers of deposits, layers that are maybe 10, 20 meters thick, and there may be half a dozen of these layers. There are places shown in green where the surface is not smooth, but rather rugged and very much pitted, as you'll see in some later pictures. And then finally, in orange, there are places where the surface has clearly been eroded, and material which previously had been below the surface is being exposed for the first time. So a lot of geological complexity. And that became obvious in 2005 with Deep Impact. Now, of course, the main point of the Deep Impact mission was to do an impact experiment and to try to determine what the mechanical properties of a comet's surface were by creating an artificial crater and seeing how large the crater was and what the morphology of the crater would turn out to be. Now, I think as most of you know, the Deep Impact experiment was a little bit too successful because the impactor did indeed hit the surface. A lot of material got ejected. In fact, so much material that the Deep Impact spacecraft was never able to see the actual crater itself. And that's where the second of the two missions in the title, one was Deep Impact, the other one Stardust-NExT, comes in, because Stardust-NExT was an attempt to go back to this very interesting nucleus and, in a sense, complete the Deep Impact experiment by looking at the impact site and seeing what Deep Impact had actually done. So let me just give you a very, very brief history of the Stardust-NExT mission. It involved reusing a previous NASA spacecraft, Stardust, and you may remember that Stardust flew by Comet Nuclei in 2004, and its objective was to fly through the coma and using cells of aerogel to actually collect some of the coma dust, enclose it in a capsule, and that capsule was returned to Earth in 2006. And those of you who have been to the National Air and Space Museum in Washington you can actually see the capsule there on display. But the point here is that the main spacecraft that carried the capsule stayed in heliocentric orbit, and we proposed to NASA that this was a spacecraft that we could use to go back to Tempel 1 and complete the Deep Impact experiment and do some other neat things. And that proposal was accepted in 2007, and so that's the origin of the Stardust-NExT mission that I'll be talking about. Now, why do you want to return to Tempel 1 to have another look at it? Well, I think some of the answers are kind of obvious. I've already mentioned two of them. One is you have an extremely interesting geological object. You've only seen about a third of it, so obviously you want to extend the coverage. And just jumping down to the last bullet, obviously you want to finish the Deep Impact experiment by looking at the impact site and seeing what kind of crater was actually made in 2005. But equally important is the fact that between Stardust-NExT and Deep Impact, the comet has gone around the sun once, and for the first time ever, you get to look at a comet surface and see how much it changes and where it changes between perihelion passages. So these were the sort of three main objectives of the Stardust-NExT mission. And that was a very successful endeavor. The encounter occurred on February 14th of this year. We flew by the comet at 178 kilometers to get as good resolution as possible. What I'll be showing you are results from only some of the images, images taken within 4 minutes of closest approach, which have a resolution of between 10 and 20 meters. The best one's about 11 or 12 meters per pixel. The spacecraft, in addition to a camera, also had two dust experiments to measure dust flux, particle sizes, particle composition. I will not be talking about these in my talk because I'm focusing on the geology. So I'll be entirely focusing on the results from the camera. So to really do the job we wanted to do, we had to arrive at the comet at precisely the right time. Remember, the comet is rotating, and what we want to do, one of the things we want to do, is to image the Deep Impact site. So we had to pick a time when we were flying by the comet, when the impact site was underneath the spacecraft and visible. And this series of this pair of pictures just shows you that we succeeded in doing that. This is the Deep Impact we've seen before. The actual impact site is right here between these two circular features. And this is the image of Stardust-NExT, where basically we managed to get there exactly when the impact site was directly below the spacecraft in an optimal viewing position. So that was done very, very successfully. And I'm going to just show you a sequence of images taken during closest approach where you're sitting on the Deep Impact spacecraft looking at the comet as we fly around the comet. You'll see different parts of the surface, not because the comet is rotating in this short time, but because the spacecraft is actually flying over the limb. So in this first view, you're basically seeing what Deep Impact saw. You see some smooth flow areas. You see some rugged terrain over here. And as the flyby progresses, we're going to be moving over the limb here and seeing more and more new territory. So just a little bit more new territory over here. And now this is the deep impact region. And we're beginning to see a high ridge here. And some of you can probably discern that there are lineations here suggesting that this high ridge is made up of layers. In a minute here, I'll tell you a little bit more about the elevation differences involved. And we'll just continue here. And now we're kind of looking down on the ridge, and we're beginning to pick up some new regions over here, which look much flatter and smoother. Here is the ridge. And now we're beginning to see some interesting things where there are terraces that are apparently being eroded and large expanses of smooth terrain over here. There's a large area that is very, very smooth. There is another air flow here, which is coming down in this part. A lot of interesting and very diverse geology. So that's basically what we saw. Let me just sort of go backwards one more time and go back this way. So what does all of this mean? Well, first of all, we've extended the coverage of the surface well beyond what deep impact did. This is shown in this Mercator map. This basically is the part seen by deep impact. This is the new area that was imaged by Stardust-NExT. So we now know more of what the comet looks like. And more importantly, we can now derive a very accurate shape model of the nucleus and also measure elevation differences. So what you're looking at here is a complete shape model of the nucleus of Tempel. Again, the radius is about 3 kilometers. The blue areas are low. The red areas are high. And let me just point out that the difference between some of the highest areas and the lowest areas is about 850 meters, which on a 3-kilometer radius object is actually significant. And we'll come back to these elevation differences and their geological implications as we proceed here with this discussion. So let's now look at some of the geological aspects of the nucleus that I briefly mentioned that we suspected were of interest from deep impact coverage and see how much more we have learned from Stardust-NExT. So first, let's look at some of these smooth flow-like deposits that I mentioned. We now know from the combined coverage that about 30% of the surface is covered by such flows. If you actually map them on a Mercator projection, the resolution here is not very good. But basically, this is the Mercator map I showed you before. And just call your attention to the little sketch map here, where there are 4 regions identified, S1, S2, S3, and S4. And these are areas where the surface is covered by smooth flows, material which apparently was erupted from the subsurface, has flown downhill to actually fill. Notice where these things are. They're in the blue areas, the low points on a nucleus, a point that I will emphasize again in a second. Here, for emphasis, are some of these smooth areas. I mentioned that some of these, such as this one, which you'll hear more about, which we call S2, was seen both by deep impact and by Stardust-NExT. And so this actually provides the opportunity to see what has changed in the 5.5 years between the 2 perihelion passages. And I will show you some of those results in a few minutes. Now, we also, as I mentioned before, discovered extensive new areas of smooth terrain on the other side of the comet. And if you kind of look at this part of the comet very, very carefully, you will see, if you really look at it, that there are indications of a series of successive flow. There are different flow margins in here. There also are exposed higher places, little mesas, maybe 25, 30 meters high, suggesting that not only has there been a succession of flows, but between the flows there has been some erosion, which has eroded previous surface, and then other flows have come in. Up in here, you will see probably what is the most recent flow stratigraphically. I'll show you a close-up of that on the next slide. This is what one of these features looks like. It's very, very smooth. This one's about 1.5 kilometers long. It's about a couple hundred meters wide. Very, very smooth on top. And the elevation difference between the top here and the bottom is about typically 10 to 15 meters. And again, topographically, this is downhill. Okay, stuff has come out and uncovered the surface. So what do we have here? All right. Well, as I mentioned, the important fact about these smooth flows is that if you actually map them onto the topography, they all occur in the lowest areas on the nucleus. And that is significant, and we feel that what that basically tells us is that this is consistent with this model I mentioned already, that we are looking at material that has come from the subsurface. So here are just, here is a summary that the smooth areas, as I mentioned, covered about a third of the nucleus. They all occur in gravitational lows. They do display different degrees of flow morphology. S3, which is the big flow that was discovered by Stardust-NExT, definitely shows evidence of multiple flow events, and all of these appear to be undergoing active erosion, as I'll emphasize in a minute or two. The very important point that I'll emphasize here for the last time is that since all of these smooth flows occupy the lowest points on a nucleus, they must be geologically fairly recent, because in fact they know where the low points are, so they have been in place after the nucleus has attained its current shape. And in a minute we'll talk a little bit more about whether or not we can place any more definite limits on the age of these particular features. Now, in terms of models, what is going on? Let me just mention one model that has been published and discussed quite extensively by Belton and Meloche. This involves the idea that a comet nucleus may be mostly made of water ice, but it also has some more volatile ices in it, things like carbon monoxide, carbon dioxide, and also that some of the water ice may be amorphous. And as a comet's surface evaporates and heat from the sun gets deeper and deeper, a pocket of amorphous ice may suddenly turn into crystalline ice, releasing energy, and at the same time evaporating the more volatile ices, carbon monoxide, carbon dioxide, from the interior. And in the Belton and Meloche model, this is what they basically envisage, that the flows that we see on the surface have been caused by the transition of amorphous to crystalline ice, releasing energy, providing heat, which then releases the volatile carbon dioxide or monoxide to the surface. The gas carries with it particulates. Once you get to the surface, the gases escape. The particulates, in spite of the very low gravity on the comet, actually stay on close to the surface and flow downhill. So that's basically the model, and I just summarized it in words here, that the eruptions are caused by the release of CO. They could be episodic because as the surface of the comet is lowered by sublimation, different pockets of amorphous ice get heated. The energy source I already mentioned is the conversion of amorphous ice to crystalline ice. And the most interesting thing is that dynamically, this comet is known to have changed its perihelion distance fairly recently. According to calculations by Don Yeomans and his colleagues, until about 1609, the perihelion distance of the Tempel 1 was 3.5 AU, where things are fairly cold. But 400 years ago, the perihelion distance was changed to its current 1.5 AU, where things at perihelion get fairly warm. And so there really is good evidence that some of this activity that we see, which geologically looks fairly recent, actually dates back only from about 400 years. A very, very interesting conclusion. Moving on to sort of the next topic of geologic interest, mentioned that deep impact found areas where relatively thick layers of material were exposed. And the new coverage of Stardust-NExT reveals several other areas where this is the case. And so let me just say a few words about what we think is going on here. A few minutes ago, when I showed you the flyby pictures, I emphasized this area, this very high area, 850 meters from here to the lower area over here, which shows these striations, which could be interpreted as a stack of layers. And we see this sort of thing in several places on the nucleus. And it has been suggested that perhaps some of these very thick layers date back from earlier period, perhaps from the actual accretion of the nucleus. So let me sort of say a few words about that. Here, going back to the topography model, the dashed red lines show you where the very thick layers are. So for example, this very high area on a nucleus is all thick layers. And interestingly enough, if you look down here, the exposures of the thick layers sort of seem to occur on the sides of the nucleus, both over here and over here. Now, again, we don't really know exactly what produced these layers, but a model that has been suggested is that these thick layers actually date back from the accretion of the nucleus itself. And the model proposed by Mike Belton and his colleagues in a different paper suggests that comet nuclei such as Tempel 1 accreted from the collisions of smaller planetesimals, objects which were very, very porous, and collisions occurred at very, very low velocity. And so the question is, what happens when a very, very porous object hits another very, very porous object at very low velocity? And this process has actually been modeled recently by Eric Asfog and his colleagues. I will show you the results of a simulation in a minute, but the results seem to imply that at low velocity, when objects hit, you can actually produce the kinds of layers that we see on Tempel 1. Well, let me just go to those and then I will come back. So this is the question: what happens when one very porous object hits another very porous object at low velocity? And the simulations, these are not cartoons, these are actually results of numerical simulations. This is what Eric Asfog and his friends find, is that you get this kind of behavior. So this is what Belton and his friends have suggested might be producing the thick layers on this particular nucleus. It's these types of collisions. Now, that looks good. The problem is that in any particular area, we see multiple layers, as many as 5 or 6 in a different place. So if this model is right, it suggests that this kind of process occurred repeatedly in the same place 5 or 6 times, which perhaps is somewhat unlikely. So maybe we don't really know what the origin of the thick layers really is. So let me move very quickly on to something I mentioned before, to the opportunity provided by Stardust-NExT and Deep Impact to look at changes. Where does a comet surface change as it goes through perihelion and isosublimate? I am not going to read all the numbers on the slide. What it basically says is that we know from observing gas and dust that goes into the coma how much material is lost per perihelion passage. And if, as we suspect, it only comes from restricted areas on a nucleus, then there is a chance, even at a resolution of 10 meters or so, to actually see the changes. And so that was one of the objectives of the Stardust-NExT mission, was to compare deep impact coverage with Stardust-NExT to look for such changes. And we were successful in imaging about 20 square kilometers of common territory between the two encounters. And the results are very, very interesting. The important result up here is at the resolution of Stardust-NExT, 10 meters, 12 meters per pixel, most of the surface is unchanged. It doesn't change in albedo, it doesn't change in photometric properties, it doesn't change in morphology. Yet, there are a few places where you can see significant changes. And remarkably, they occur at the edges of these smooth flows that I mentioned before, particularly this region called S2. So there are significant changes when stuff is sublimating from the surface, but they are very, very restricted. And just to jump ahead a little bit, they seem to be restricted mostly to the edges of scarps. So let me just show you as an example the evidence for this particular series of changes here. This is the same area S2 seen by Stardust-NExT in 2001, a deep impact in 2005. And this particular edge, the left-hand edge, is emphasized over here. The arrows point to places that have changed. I'm sure you have trouble seeing this, so I'm going to twist one of these around and just show you one particular example. Again, here we have a deep impact image. That's the edge of that smooth flow. And just concentrate on this promontory here, this thing, which has completely disappeared. This is about 50 meters in dimension. The thickness of the flow here from stereo is about 10 to 15 meters, so you can estimate the amount of material that has been lost. And in the next slide, I have some numbers, which again are not really important, but the point is that in this particular small segment of the scarp, enough material is lost to account for about 3% of the total mass loss from the comet. And of course, there are lots of such scarps on the comet. And so a significant result is that in this particular comet, the mass loss seems to occur mostly from the edges of scarps at the present time, and a lot of the surface is inert. And that is very, very interesting. Now, the other thing you can do, coming back to the age of these features, is from the rate of recession that's observed in this area, you can estimate how long this flow will last before it completely sublimates away. And here are just some numbers that at the recession rate of some 50 meters per perihelion, say, it might last something like 60 orbits, which is like 300 years. So these are very short time scales. So there are interesting things going on right now on a nucleus of a comet. An important thing to emphasize in this slide is that in spite of the fact that there are scarps that are retreating, materials being lost, the albedo of the surface does not seem to change. The general albedo of the nucleus is about 4% everywhere, even in the places that are losing material. And another thing to emphasize, and this is mostly based on deep impact results, is that there are very few places on this nucleus or other nuclei of Jupiter family comets where water ice is actually exposed on a surface. This is a deep impact result from 2005, and the blue areas here are the only places on the nucleus where a little bit of dirty water ice is actually exposed. The rest of the surface is black and ice-free. Okay? And this is a result that was extended to another 60% of the surface by the Stardust-NExT results. So mass loss is occurring, but the nucleus remains black. That's a very interesting thing to think about. Okay, just a couple more points of geology before we kind of summarize the big picture here. Several times I used the word significant erosion, so I want to use two slides just to emphasize that point. Here is the Stardust-NExT face of the comet that you've seen before, and just want to point out to two things I mentioned before. There is an extensive scarp here. I think those of you who are close enough can see that actually it's terraced. There are about 5 steps here. The elevation from here to here is between 60, maybe 100 meters or so. So these steps are about 10, 20 meters high. But clearly this region is eroding, and you'll see additional evidence of that in a minute. I've already pointed to the smooth region, which protruding from the smooth region are isolated mesas, if you like, which are about 20 or 30 meters high, suggesting that in this region, 20 or 30 meters of material has been lost through erosion. There are other examples of this sort of thing. Now, one thing that is remarkable about the scarps on this comet is that they occur in a large variety of different morphologies. And so I have one slide just to kind of try to summarize this. The point being that not all scarps have the same morphology. There are scarps on a comet that are terraced. There are scarps that are scalloped. There are scarps that are almost vertically abrupt. There are some that are concave. Now, what does that mean? Well, what that means is that material in different places is eroding in different styles. That can only occur because the material is either different in these places in composition or in texture, physical properties, or both. So that's a very interesting conclusion. The surface of this comet is not homogeneous everywhere. Just to finish up on the erosion part, let me remind us that the most significant aspect that suggests that material is coming off the surface is in jets that are visible in the coma. And the pictures I've shown you up till now have been processed to emphasize the surface of the nucleus. These have now been processed to emphasize the jets that are coming off. And one of the things that we tried very hard on Stardust-NExT is to obtain enough coverage in stereo to be able to trace back to the surface where these jets are coming from and see if we can connect the jet activity to what is going on the surface. Before I show you the results of this, let me just mention that jets were seen both on Deep Impact and on Stardust-NExT. The activity in 2011 was a little bit less than what was seen by Deep Impact in 2005, but that's not really a significant difference when you realize that Deep Impact flew by the comet almost exactly at perihelion when the comet is most active, We on Stardust-NExT flew by the comet about a month later when some of the peak activity around perihelion had begun to decrease. So I don't think that the difference in the level of activity is very, very significant. But what is significant is that we can, because of our stereo coverage, triangulate the jets and take them back to the surface. And that's very interesting, and here is the result. This is the face of the comet we've been talking about. This is that terraced scarp that I mentioned several times. That is clearly, from a geological point of view, eroding. And here in this box is the source area of 8 of the 12 jets that we see. Okay, so clearly the jets are, as far as we can tell, associated with this particular scarp, which is actively eroding. Another example of the fact that the activity on this comet seems to be focused largely on what is going on in the scarp areas. Well, just to conclude the geologic tour, let me mention the other parts of the comet, which I haven't talked about very much, the so-called pitted terrains. And those of you who can cross your eyes, this is actually a stereo pair of part of the comet that shows you the areas that aren't smooth, that have this very, very pitted appearance. To some people, it might look like a heavily cratered, eroded crater region. So what is actually going on? Well, the pitted terrain is very, very interesting. It covers about 50% of the surface of the nucleus. And these pits range in size from our limited resolution to hundreds of meters. The largest one's about 800 meters across. They have very different morphologies. And what's interesting, if you actually plot a size distribution, it looks very much like a crater population with a cumulative slope of -2. But don't get carried away, because it is extremely unlikely that these pits have anything to do with craters. And why? Impact craters. Why? Well, one significant reason is that people have done very serious calculations about what the impact rate on a typical Jupiter family comet might be expected to be during its lifetime. I'm going to specifically refer to results by Duncan et al., where for a comet such as Tempel 1, which might last for a couple thousand orbits in its current orbit or so as a Jupiter family comet, the number of impacts that you expect is a handful, 1 to 10. There are hundreds of pits on Tempel 1, so something else must be going on. So what else is going on? Well, what else is going on? Well, let's go back to the idea of materials that are more volatile than water ice, carbon monoxide or carbon dioxide. And again, this involves our friends Belton and his colleagues. And again, the suggestion is that as heat propagates into the comet, pockets of more volatile ices are evaporated, and those gases work their way to the surface. In some cases, in large cases, they may produce the flows we talked about. In smaller cases, bubbles of gas might reach the surface and basically just blow a piece of the surface off, making a pit. Or if the activity is more pronounced, material might escape in a particular area for a period of time, making a deeper and deeper pit. And that currently is our best idea of what produces the pitted terrain. Again, there are too many pits for these things to be impact craters. So we think that the pits are probably related to these things called mini outbursts. And if you watch the activity on Tempel 1, the comet does have occasional bursts when stuff comes up into the coma, mini outbursts. You can calculate from how much stuff is produced in a mini outburst, how much of a pit you need. And a typical size I mentioned down here is a pit about 30 meters or wide, which is kind of consistent with what you see. So that is our best estimate of what is going on. Now, one thing I've been leaving till the end is, what did we learn about the deep impact experiment? So this is my last item before we get to the conclusions. And the point I want to make, I think I've already made it at the beginning, is that we worked very, very hard to make sure that we've got a good image of the deep impact site. And we flew right over it, and we know exactly where the impact occurred, because as is shown here, the deep impact impactor had a camera, and as it headed towards the surface in 2005, it took a series of nested images, and so we can locate that site. I set up here to 100 meters. Actually, the number is about 25 meters. So we know exactly where we hit, okay? And we did obtain the best possible images of the impact site at resolution ranging from 12 to about 20 meters per pixel. So we did our job, okay? Now, I'll show you what the result is. It's not very spectacular, and as I generally say, it's not our fault on Stardust-NExT. It's the fault of Mike Ahern on Deep Impact, because he just did not make a big enough crater, okay? So here is the result. So this is the Deep Impact image. This is the Stardust-NExT image. And if you look very, very carefully, and if you are a believer, you can actually see there is a dimple in here. And perhaps it's a little easier to see in this different processed image. What we're referring to is this thing right here. That was not there before. There's a little dimple in here, which is about 50 meters across, okay? Now, you can do something interesting with that. You remember the objective of Deep Impact was to try to determine the mechanical properties from the size of the crater that was made, because you know the impact energy. So I'm not going to go through the details of this. Let me just say that we have experts on the Stardust-NExT team, Jim Richardson, Peter Schultz, J. Malash, who claim that they can calculate the size of a crater for an expected impact energy given the material properties of the surface. So what is the result? Okay, so the result of plots such as this is summarized right here. The crater seems to be about 50 meters across, and that is consistent with an impact into a surface that has the mechanical properties of, quote, lightly packed snow. Actually, what they claim is lightly packed mountain snow, whatever the difference is, I don't know. The issues, of course, is that we have seen this, we saw this crater 5.5 years after the impact. So the question is, you know, was the original impact crater bigger? Did it get modified quickly by collapse? Has it been modified by sublimation in the intervening 5.5 years? We really don't know. But on the basis of what is there, this is what we can conclude about the surface properties of the surface. So now, folks, we come to some conclusions. If you have been awake, all these things are obvious. If you haven't been awake, now is the time to wake up. So conclusions, first of all, at least this particular comet is not just a bunch of little snowballs and dirt that are packed together. This object is globally layered. There are smooth flows on the surface which demonstrate that the nucleus has undergone and continues to undergo, because these things are changing, okay, a significant geological evolution having to do with processes that are internal, things that are happening below the surface. We see a lot of this pitted terrain, and there's just too many pits for this stuff to all originate as impact scars. So something else must be going on, and we think that many of these things are produced by these many outbursts and then subsequent sublimational erosion. Another one of our conclusion is that scar retreat is a significant process on this particular object. And I've tried to show you that as far as we can tell, many of the jets that we see have their source at the foot of these retreating scarps. And interestingly enough, in spite of the fact that material is being lost, significant amounts of material being lost in these isolated places, those places remain black. The surface layer of black crud doesn't seem to go away when you sublimate material. So that must say something about how thick that layer is. And significantly, there are almost no exposures of clean water ice on this nucleus or from other missions on the nuclei of other Jupiter family comets. And as I quickly mentioned, in terms of completing a deep impact experiment, we know exactly where the impact site is. We've located that scar. I told you the size of it. And one thing which I didn't mention, which I should mention, is that there's still one part of the deep impact experiment that is not complete. People who do modeling of cratering have argued for years of what is the morphology of a crater that you make on a porous icy object such as a comet. What does it really look like? And that was one of the things that Deep Impact hoped to answer. But because the Deep Impact crater, for our resolution, is so small, we really can't obtain any information about its morphology. So this question remains unanswered. So in summary, let me just look towards the future and the future of comet exploration. One of the things we all want to do is to return a sample from a comet. And years ago, when I started doing this, and I proposed sample return missions, reviewers always told me, well, you can't do this because we know nothing about our comet surface, and you can't sample a damn thing because it's as hard as concrete, and it's rugged, and you just can't do this stuff, okay? Well, let me point out that we have made some progress here, because we have a comet, Tempel 1, where from the size of deep impact craters and from some other things, we know that in many places you're dealing with a loose, porous surface, like mountain snow. Easy to sample, okay? There are extensive smooth areas. 30% of the nucleus is covered with smooth areas, which are smooth really at the scale of better than a meter from the photometry, okay? So it's very easy to land. And so I claim that Tempel 1 is an ideal target for a comet sample return mission. And allow me just to say two more things in conclusion. One is that I began to talk by pointing out that in any learning endeavor, there are sort of three steps where at first you think you know everything, and then you get confused because you get a lot of facts, and then hopefully you begin to understand the facts. We're clearly at the second stage, but I think we're making rapid progress towards the ultimate stage of really understanding comet nuclei. And I fully expect that in the coming decade, because of missions such as Rosetta and follow-on missions such as comet sample return missions, we will get to really understand what comet nuclei are like. And my last slide is a cautionary slide, because I focused my discussion on Comet Tempel 1 because that's the comet that I happen to know the most about. But one of the things we know from the few comets we have looked at is that not all comets are alike. Here's just a picture of Tempel 1 and another comet seen by the same spacecraft, Hartley 2. And although this is not the time to discuss it, geologically, these things have profound differences. I mean, for example, there is no pitted terrain on Hartley 2. There are no smooth flows on Hartley 2. So we have to allow for the fact that there are still many things we have to learn about comets. Comets are very interesting, and it's a great adventure. And I think we are all fortunate to be living at a time when comets are more than just points of light or little streaks of light in the sky. They're objects that we can actually send our spacecraft and instruments to and study them in detail. And that's why I am very optimistic that a lot of these questions which I raised this afternoon but could not answer will be answered by some of you in the next 10 years. And with that, I thank you very, very much. Oh, yeah, sure. As long as they're not difficult.
That's right. We have some time for questions.
It's
Phil.
Joe, thank you. First of all, thank you very much. This is a great overview. A question, those jets, what's the velocity of the material coming off? Can you say anything about then the dark material that they don't entrain? Does that mean that stuff has to be fairly coarse grained?
okay. All right, let's take these in steps. I think the first thing that's sort of useful is that the escape velocity from Tempel 1 is millimeters per second. Okay, the jets are coming off at 100 meters per second. Okay, so they're actually leaving, and they are entraining material. I mentioned that we have two other instruments on board, including a dust counter. You can actually see the dust, coming off. So, as to the best of anybody's ability, about half the stuff in a jet is gas, half of it is probably dust. Okay. In the images, of course, it's the dust that's scattering light. So that's really what you're seeing. And now, the simplest answer of why the surface remains dark is that apparently that surface layer of crud is pretty thick in most places. Okay, and then of course the question is, how do the gases actually escape through that? And it's, I don't know the answer, okay, but I think it's an interesting observation that when stuff comes off, you don't suddenly see bright ice.
Do you have an estimate of the mean nucleus density based on...
Yes, yes. Yes, the question is there an estimate of the nucleus density? And I forgot to mention that, but from the deep impact experiment itself, you can see the ejecta curtain spreading, and in part, the rate at which it spreads depends on a local gravity. So back in 2005, the surface gravity of Tempel 1 was determined. We also know the size of the nucleus, as you saw the shape of it. So you get the mass. You can, you have the gravity, you have the size, you can get the mass, you get the density. Answer is 0.35 grams per cubic centimeter, 35% the density of water. So it's the nucleus as a whole is very, very porous.
I would like to mention that it is exactly the value that was obtained for Comet Nuclei from the emission.
Yes, that's a true statement. In case people can't hear, I think the comment was made that there was an estimate from Halley, and that's a very similar number. Yeah, that's right.
How do you make amorphous ice?
Oh, okay. That's an excellent question, and I began by saying that I personally am not convinced that amorphous ice exists in Jupiter family comets. Okay, but I'll tell you the religion. Okay, it is claimed that if you condense water vapor at low pressures, and do it very quickly, that it doesn't have time to actually form crystals, and you form a glass, okay, and that basically, if you then provide heat and time, it'll start to crystallize, and it's an exogenic process that releases energy. Okay, that is the claim. Okay, now the reason I said I'm not a great believer in this is because in my youth I used to do thermal calculations, and I have convinced myself that it doesn't take long for a Jupiter family comet, which orbits inside the orbit of Jupiter, for hundreds of meters of the surface to reach a temperature higher than 110 degrees or whatever the magic number for conversion is. Okay, so I personally find it hard to believe that there is a lot of amorphous ice in the near surface of a Jupiter family comet, but there apparently is some source of energy that's driving all this. But it's a good question.
One more?
Wasn't there anything learned after the material that was ejected from the rocket on Deep Impact 1?
Was there anything that was learned about the ejected material? Sort of two important things. One, of course, is that there were spectrometers both on board the Deep Impact spacecraft and on other spacecraft observing the comet from large distance. And so one of the major results from Deep Impact is as the impact proceeds and material gets ejected from deeper levels from below the surface, you get more volatile material, more volatile ices, and more organic material. The first stuff that comes off is basically dirt. Okay. Shortly after, what comes off is a lot of water vapor. Okay, and only then do you get carbon dioxide, carbon monoxide, and unspecified organics, because you can only see the stretch from CH. Okay, so that's one result. The other result is the one we kind of mentioned about the ballistics, which tell you, I mentioned the gravity, but there's also information in there about the mechanical properties of the surface independently of the size of the crater. So the Deep Impact experiment actually told us quite a lot about the surface.
Thank you.
Thank you.
So two things before we thank Joe again. One is that we have the room for a few more minutes, so I welcome you to come up and personally congratulate our Whipple Award winner. And the second is I hope to see you all back here tomorrow morning, bright and early at 8 o'clock for our Sagan lecture to learn about exoplanets. Let's thank Joe again for a fabulous talk.
Thank you.